Hello, ladies and gentlemen, children of all ages. Welcome to our new lecture in data analytics. This lecture is, of course, illegal because it's live being happening during the juvenalia. But of course, as we've arranged, this video will be available for you all the time. We've started our transmission a bit later, so lecture will be a bit shorter today because of technical problems with starting the stream, but hopefully those technical problems won't be coming back to us after everything. So last time we've covered the initial ideas of how to construct likelihood, how to construct models, to cover the workflow of creating a model. We've discussed containment priors, so how to select priors to keep our values in reasonable places. Today we will cover, first we'll start with the aspect that there were questions about how the exam will look like. Because of the multiple issues, we are doing it with a more relaxed form than in the previous years. We'll see how it works. Then we'll discuss multi-parameter models, and actually we will discuss new methods, new likelihoods that we can use to create our models. So we will be moving to more and more complicated structures of the model in order to solve our problems. So let's first start the exam. As we've arranged with the group heads, our exam will take a form of discussion about the projects, because I've decided that because of some delays in the lectures, it will be unfair to you to require for you to be able to answer all the questions on theory, and let's more focus on the application. So during the entire lecture, the entire exam procedure, we will be discussing how you created or solve your problems. As we've stated, the projects that you are doing now require from you select the phenomena that you are interested in, that you want to model, propose different competing models that can explain that phenomena, because we don't know really we not always know which models are the best. Maybe more complicated models are better, but there's a risk of overfit, or maybe a less complicated model but more robust to disturbances. So we'll discuss it also today, some kind of models. For those models, you of course have to formulate certain assumptions which will transfer into your prior selection. Then you will do your checks of your prior. So I will be asking you about what was your process in selecting those priors, what were your assumptions. So you will be required to defend your model, why the model that you proposed is good or not. Then we will discuss how the computation occurred. So you will have to explain what tests were being done for the computation, how the computation was done, or whether any issues with chain mixing, or whether any issues with divergences. Have you done anything about those divergences? We will discuss how the model works on the in the aspect of your representing the data. So we will discuss what kind of summaries you've analyzed and why, in order to verify the model. And then, of course, we will want to do some model comparisons. So you'll be comparing models using the information criteria and the lymphonoid post-validation. So it would be good that you would be able to explain what's going on there also. So the most important aspect in this analysis, of course, actually will be you defending your model and your selections of structures, of priors, of how you did and why you did your analysis. So this will be a discussion of how you are doing Bayesian analysis in your problem, focusing on the entire process of deciding how the model being created. So more about thinking in Bayesian modeling way, less in the scope of definitions and the theorems and stuff like that. So those things you will be using them indirectly during your modeling, but generally we'll be focusing on how well you understand what you've done in your model, why you did certain things. So this will be the exam questions, and of course you will be answering to in your project pairs unless someone is doing the exam, the project individually. So they will be also examined individually. Okay, so this organization aspect finished. It would be very nice if someone would create timestamps when they will be watching this video, so for others to be able to find this part. And now we can move to actual new, more advanced likelihood to represent our models. Previously, we've considered Poisson distribution, binomial distribution, so very simple, very simple exponential distributions. So we've seen some examples how it works, and we've did the model for flight of the for airline accidents, so you can see how it works. I will not be covering now the kidney cancer example I've mentioned last week, because I will want to do it in the context of hierarchical models, which will follow in either this or in the next two lectures. So this will be the more advanced idea, and will show how the hierarchical model can be represented. So we will be now not discussing the cancer model, right? Let's focus on the multiparameter models. And generally, we are focusing on represented parameters. As we know, parameters can be functions of other parameters, which we can do in multiple ways. We'll cover it hopefully today. But generally, our model is represented by multiple parameters, which express some understandable or ununderstandable, observable or unobservable quantity, and we are not always interested in all of them. For example, we might be interested only in the mean of the sample and not necessarily in the aspect of others. So forgive me 1 second. I must do a quick break to do some signing, and we'll be back in a Okay, I'm back now. Sorry for the disturbance. I'm still not sure why we don't have the camera for the so you to see me, but well, we cannot do anything. We can do everything because I'm not sure why it's not really happening. Maybe I can change that. Okay. Oh, now it should work, so you can see me that I'm at AGH. Maybe just some light correction. I have to compensate for the sun. Okay, now you can see me. This will be the place will be the exam will be also occurring. Okay, so let's return to the scope of what we are talking. The main issue in having multiple parameters, that when we are interested only in few of them, is that we have the we can marginalize them. So we can focus only on parameters of interest, like for example, the mean of this of the distribution, or standard deviations, or variation, or whatever else that we want. Or for example, mean of just a subgroup of variables. In basic statistics, we can just marginalize them. We can use the entire model and focus on the only on the subset of parameters, which of course is being done by sampling the entire distribution and focusing on the limited amount, the samples of only certain parameters. Which is of course generally the aspect of splitting a vector of parameters, formally theta1, theta into part of we are interested in and part we are not interested in, and in normal distribution, like when we are interested, which is normal y conditional on mean and standard deviation, we are often interested only in the mean. And formally, of course, as with all other procedures, we just take the joint density and we average over the non-interesting parameters, which numerically is done through the sampling. So generally, we are averaging out those things that we are not interested. And this sometimes we can do numerically, sometimes in certain cases when parameters that we are not interested are discrete, we will want to do it analytically, because then generally our model becomes just a, for example, our probability distribution will just be a sum of different probability distributions. This is important because generally Markov chain Monte Carlo and discrete parameters do not work well together. If we have discrete parameters, there's a problem to how to include them into the sample as a typical set, and how to move from one discrete value of parameters, like for example 0 and 1, between each other. And this can be solved by marginalizing analytically those discrete parameters and create a model that incorporates all of them. That's the way, for example, mixture models are being created. But let's focus on something simple, like a normal data with a non-informative distribution. So another option of priors that we've mentioned before, but here we have an example. A non-informative prior is a prior that introduces no information into the model. So we do not want to add any kind of regularization and to add some kind of meaningful prior. With parameters that are representing a general location of our data or general value, the uniform representation is often enough to express our complete ignorance. Because if we have complete ignorance of the over the mean and saying sampling it uniformly, so then there is not a problem. However, regarding variance, the uniform representation of variance is not really, or standard deviation is not something that is really useful. Why? Because the problem for our parameters is that the variance of standard deviation corresponds not to the spread of the distribution, which in particular relates to possibility of it spanning multiple orders of magnitude. Like in automatic control, we have logarithmic magnitude phase characteristics. We are often interested also in very low frequencies, which on a linear scale take a very small part of the real axis. So like the values between less than, let's say, 1 Hertz take much less on the linear axis than, let's say, up to 1000 Hertz. So, but on a logarithmic scale, they just are split into each octave representing each power of 10. So, in order to express our ignorance of variance, we need to be ignorant not only about its actual value, but also on the fact that we are not really aware which order of magnitude is here. That's why the best option for that is to assign a uniform prior on the logarithm of standard deviation, because in that case we know that there is a complete possible spread of multiple orders of magnitude, which generally gives us a joint prior for mean and standard deviation of the or the square of standard deviation of the probability distribution as proportional to 1 over squared sigma. And that using multiple computations allow us to create a joint posterior distribution which is generally proportional to the likelihood just multiplied by sigma squared. What is very nice for normal distribution, and this is something that generally is being practically used in many cases, I'll just move myself somewhere else, is that often the normal distribution can be analytically factorized, or especially in multidimensional cases where a lot of computation can be simplified by appropriate modification of matrices to get results we want. In case of scalar stuff, we can actually simplify our likelihood because all the information about the data can really be summarized using just two numbers, which is sample mean and sample standard deviation, and sample variance. So those things are called sufficient statistics, and they are simplifying our model significantly because we do not have to work on the entire data directly. And we can, of course, work on this posterior distribution to get our conditional probabilities of mean or standard deviation. So the marginal probability of, so the conditional probability of the posterior distribution conditional on sigma squared and measurements is the number of measurements, sigma squared, and the expected mean. In case of marginal posterior for sigma squared, it can be computed through this integral, which is a bit difficult. However, it is a so-called normal integral because it is this function is proportional to this kind of normal distribution. Or not normal distribution, but a special kind of distribution, which really is a form of a scaled inverse chi-squared distribution, which for us, the only thing that we want to know about it is that chi-squared distribution is a distribution that can be easily implemented. So, for example, this can efficiently improve our factorization. What does it mean? It means that in case of normal distributions or no distributions that are similar to normal or at least partially, we can exploit the structures in order to create more advanced, more efficient sampling schemes, which is not something that we use for small data. For big data or large amount of data, it's something that needs to be generally thought about. This is the aspect that really works on it, that if we can take our joint posterior and practically factorize, because formally each joint posterior is a joint distribution, it can be represented using the appropriate theorem of the regarding the probability of joint distribution, that is always a product of the conditional, the one parameter conditional on the second and the second. However, in case if this can be computed, that the joint posterior distribution can really be factorized in those aspects, and especially if part of them are normal, then it is a very, very beneficial situation. Look at here, the conditional posterior of me on those two is a normal distribution. So having normal distributions are very easy to sample even in multiple dimensions. So this is the advantage, that if we can factorize this part, we can create an individual sampling scheme which can be efficient, and it is, for example, used in certain probabilistic libraries like INLA, which is INLA, which is the integrated nested Laplace approximation software, which is based on R, but it uses the scheme that it takes the large dimensional normal part, uses efficient sampling methods based on the sparse algebra computation for the normal distribution, and just those parts, they are approximated. So if we can get samples from this part, then we can use them to sample for this part much more efficiently. So we can marginalize over sigma squared just by repeated simulation, but generally we can generate those samples by switching the part when, for example, we have a large dimensional normal part and a small dimensional non-normal part, which is more difficult to sample, but we have little parameters, and then we can switch to more parameters too, but very easy sample. And in case of this example that I showed, there is an actual analytical solution of this, which reduces to student t distribution with n-1 degrees of freedom, location of sample mean, and scale of sample standard deviation squared divided by the sample size. And generally, this is in the case of normal distributions, and in case of generally creating posterior predictive distribution for future observation, it is again very nice, because if we can sample from, let's say, sigma squared conditional y, then we can sample from sample means, so the means of samples. So then we have the samples for me and sigma squared, which again can be used to predict our distribution, because using those posterior samples for me and sigma squared, we can just use normal distribution to sample y's. So we get a posterior predictive distribution by propagating this data this way. And in this special case, it just will be used that we can sample means using the student t distribution. So let's move to an example, numerical example of how such normal models work. And this is a very nice example, which is based on so-called Newcomb experiments. Wait a second, I just get some zoom here. So generally, we are working a very celebrated statistical example. You can find it in multiple books, among book of Gelman, the Bayesian data analysis 3. Which is, I've mentioned before, is a freely available book that you can find PDF online. This example is based on one of the earliest experiments relying on determining the speed of light, which was done in Washington by Simon Newcomb, who performed the experiment generally in a bit complicated way, estimated the time needed for traveling between 2 points, lights traveling to a mirror and back, at a distance of 7,442 meters, and 66 measurements were obtained, which were used to estimate the speed of light. And the mean of those six measurements could be computed using the just the sample average, simply like standard deviation, and you can compute analytically using formulas we've seen before, the 95% central posterior interval, which is here. What is important, what are those numbers means? They are deviations from the 24,800 nanoseconds that time scope. The problem, of course, with this model is that using normal model to represent this data requires from us a lot of assumptions for the normality, and especially the problems with outliers. So let's focus on this model instead. Let's look at the data. The data is generally well concentrated. 64 samples are very well concentrated here. However, we have two outliers of our measurements. So they are most of the samples are above 24,000 nanoseconds, but there are some that are small. And we can use a model, we can simply create a model that will fit our data using the presented non-informative priors. Because we are using logarithmic parameterization, the 1 over sigma squared is its logarithm is -2 log of sigma, which is added to the logarithmic target function, and we are adding a logarithm of normal probability density function. So y values are conditional on mean and sigma. We are adding something that you've already seen before, the log likelihood, which is something that we'll be using for model comparison. So we will discuss model comparison at the end of this example. So for our data, we just providing the velocity measurements and their number. We are fitting our model. We are doing the diagnosis of this model, which is generally okay. And let's look at the mean value. Let's compare it, first of all, using the posterior predictive distribution with our data. Of course, the problem is that the actual speed of light is a bit larger than a sample mean. And as you can see, our samples are being driven by the outliers. Okay, so we are moved away from the actual. So that the outliers are biasing our. But again, should we remove the outliers or not? This is a very important design question, because removing outliers always changes our data, and those outliers are not completely absurd, because in the scope of all values, they are not that different from the values of interest. So we are, of course, getting the results that are consistent with the analytical results that we had here, up to like a second place after the. So well, I'm not sure why it's Python. This should be Markdown, so it will look better. Okay. So generally, 2 our outliers are skewing our estimate, and we want to use it differently. And here we can consider a different model for our case. Here we can use also the Arvis posterior predictive checks, which, as you can see, are not really that better than histograms. Histograms show us samples, give us this concentration. The posterior predictive distribution from Arvis uses kernel density estimators, so we are losing tails here. Generally, there are problems with scaling values up to appropriate scale. So generally, as you've already seen, in multiple examples, using the kernel density estimates for such things is not necessarily that good. But we will now move to the student t-likelihood, because the main problem with normal distribution is that normal distribution is very sensitive to the outliers. This is relatively logical, because when we have outliers, then our mean is being strongly influenced by each large value we move outside. And the idea for more robust inference is to admit a probability distribution that will allow us to accept more values that are further away from the mean. And this is something called the fat-tailed distribution. So a distribution that allows your probability to take values that are higher, that's a larger from the mean something. And student t-distribution is a special distribution which is very similar to normal in its shape. However, it has heavier tails depending on the value of ni here, which is called traditionally degrees of freedom, which makes sense if it's an integer. It doesn't make sense if it's a real number, and it can easily be a real number. Either way, the student t distribution is a distribution which, when ni approaches infinity, it becomes a normal distribution. However, if ni is small, the tails are heavier, with the extreme case of ni equal to 1, which is the Cauchy distribution, which is a notoriously heavy tail distribution. We've seen examples of difficulties with sampling from Cauchy distribution earlier, because it doesn't, for example, have defined mean or variance. So how to, we will, of course, try to estimate all those three parameters. So we are modifying our model by changing the likelihood and adding additional parameters. And for that case, we need to assign some kind of prior for the degrees of freedom. And again, using some kind of ignorance here, we are relying on the prior choice recommendation, which is provided in the Stan wiki. And it proposes a non-informative prior for degrees of freedom, which is a gamma distribution with parameters 2 and 0.1. This distribution takes a positive value, has enough heavy tail to possibly assign large values of degrees of freedom. Our model doesn't change that much, really. Just adds additional parameters, which of course has to be a positive one. Then we use the same location parameter, so the same assumptions of complete ignorance about mi and sigma, and we are using the gamma distribution as a prior for ni, which are then being fed to the student t likelihood function through a logarithmic parameterization. And again, we are computing the required logarithmic likelihoods. Okay, so we can, of course, fit our model, compile it, run some chains without any divergences, without any issues. So the effective sample size is satisfactory, everything works. And it moves a bit our results away from the outliers, compensates from the outliers, and helps with the outliers. However, as the entire data set is based, because as you can see, even this part has a mean away from the actual speed of light, it is a marginal improvement by adding additional parameter. It's a bit better. We get a tighter confidence interval for our probe, but again, it's still biased by the data. So what can we do with that? Again, using the posterior predictive distributions, using kernel density estimates, it looks a bit nicer because the outliers are not influencing everything that much. The tails are longer, but still, again, because we have those kernel density estimators, the tail behavior is not really well modeled. But we mentioned model comparison. We've computed the logarithmic likelihood functions, which generally is as a reminder, this is a vector of values where we compute for each of data point, we compute what is the value of likelihood, logarithmic likelihood, corresponding to this exact value of y for all the samples parameters in this point in the Markov chain. So we are taking points from the chain, and for each of those points, we compute a vector of logarithmic likelihood values. And for that, we can use multiple methods of comparing the models to obtain so-called model rankings. We are using methods that are generally dedicated for estimating the model behavior outside of the sample. So we are having the samples from the we have our samples that we use to learn our model, but then how to estimate how it will behave outside. Classically, leave one out cross validation relies on the idea that we just learn our model with the entire data set except one sample, and we verify how this sample behaves. And we do it for all combinations to get the average, the statistical values of model correctness after. Fortunately, in case of Bayesian statistics, because we can compute samples of log likelihood vector for each of the Markov chain values of interest, we can estimate that using so-called Pareto smoothed importance sampling, and that gives us the possibility of estimating the model behavior and estimating the values of what would be the actual value of leave one out cross validation. And doing brute force testing, we can see that those values are often very close. What is important when we compare those models? We of course have to use the Arvis structure of inference data, which is being created here from command pi. We are using Arvis function from command pi when we need to just assign appropriate value numbers, what is what, in order to, for example, generate such plots and also to perform the model comparison. As we can observe computation of the information criteria, we can get some information that there is some issue. That is, Pareto distribution, parameter of Pareto distribution is greater than 0.7 for certain samples. And what does it mean? That means that the Pareto smoothed importance sampling algorithm has issues with the model in those highly influential observations. We generally know that they are highly influential observations because we have two samples that are much different than others. So this is the first signal that is something's going on, and we can create the ranking of the models, which we can get in form of a table or using the this nice kind of plot inspired by Richard McElrath's book. Generally, what does it mean? It means that our model is the student model is in this sense better. Those bars represent how well the model, which is let's say the uncertainty about the value of the out of sample predictions, which are given by this open circle, and black are these the in sample predictions. So this thing gives us information that we have some uncertainty for this model where the value of the estimated out of sample behavior lies, but in large consistency we can see that the values for student model is preferred. That also means that we have some uncertainty in a model comparison, and the wider overlap over those intervals, the greater risk that models are really undistinguishable from each other. And because of the data set, it can be strongly influenced. So this will be something that you will be attaching to your projects, that you will be comparing your models to see how, using these information criteria, which model is better, or because all those criteria generally want you to combat overfit, because in most of criteria we are comparing how model fits the data with some kind of estimate of the effective number of parameters in the model. In case of the simplest criteria, we just have a number of parameters. So the greater number of parameters, lower the value of the criteria is worse. So this is a lower number, more negative number. But in case of leave one out cross validation, this gives us the similar value, but numerically, but the interpretation of effective parameters is not as that obvious. What is very important is that the value of log 1 cross validation, or this expected log predictive likelihood, is that generally this autosum is uniqueless. So the fact that mean values differ by 40, it doesn't mean anything. We know that there is no overlap, so that's important, but we are not, if we, for example, have 3 models, we would not really be sure what does it mean that something is greater by 20 or by 5, or by 1,000. Those values are, again, not really interpretable. So this is the big drawback of the information criteria for model comparison, that we do not get the issues. Okay. So to get from this model is, you see how to perform the comparison, how to interpret that. Lower overlap between models, so between those intervals, the better distinguishment of the models, the higher value, more positive value of the information criteria suggests a better model. Of course, it's not necessarily true. If there are outliers, there will be some information during the estimate. Okay, so let's move to a different example. In this case, we'll move to the example of more of different distribution, because, for example, we can have a situation when we have k possible outcomes. So not binary selection, not a discrete, just a number result, but we have k possible outcomes. For example, in one mandate elections, or in the case or presidential election, we have the one winner, and this one, or people can vote for one person. So analyzing the distribution of the votes will require only position of a vote. But of course, we can also think about a classification issue, that only one category is used. So there's very multiple cases of when we want to use the multinomial model that will represent our categorical data, so that something belongs to one category. For analytical computation, we can easily use some called conjugate prior, which I mentioned before. Conjugate priors are those that give us nice analytical formula for the distributions. And as for binomial distribution, beta distribution was our conjugate. In case of multinomial, our conjugate is Dirichlet distribution, which behaves exactly as beta. However, the main important thing is, in case of multinomial, we had one parameter theta, which was between 0 and 1. In case of multinomial distributions, our parameter theta is distributed on not on an interval but on a simplex. Simplex of so the vector it will always be a vector of numbers summing up to 1, because the probability of all possible categories has to sum up to 1. And again, as with the distribution, we can use it as interpret this as a previous experience in experiment. And we will cover simple data sets of 1988 US presidential election. This is again a celebrated example from the statistical books. In this example, we had an election where we had George Bush Sr., the one who did the first war in the Gulf, so first invasion of Iraq, after Iraq invaded Kuwait. His opponent was Michael Dukakis. He was one of the he was a Democratic senator, and there was also a group of independents, or just people who decided not to vote. And we had a survey by CBS News of 1,447 American adults to find their preferences in the upcoming presidential election. Of course, actual sampling of population for such surveys is much complicated, but if we assume a simple model that just those were numbers drawn out of entire populations, those people were drawn from the entire population, then our data will follow a multinomial distribution. So George Bush, Michael Dukakis, or else. And we have three parameters that correspond to the proportions of Bush supporters, Dukakis supporters, and those of no opinion. The estimated, we are really interested in what is the probability that the first candidate, in this case Bush, will win with Dukakis. So what is the population difference in the support of the major candidates? If it's positive, so it will mean that the probability for Bush is always better than probability, higher than probability of Dukakis, which will give us the chance. Our data set, as you see, is very, very simple. It consists only of three numbers. Our model is also very simple, starting with prior predicted distribution. We'll be just using the additional package that will allow us creating nice package for visualizing three-dimensional simplexes, which only goes for those simplexes. So generally, we want to consider how our priors work. So we have numbers of categories, we have number of votes, and we have our parameters. Parameter theta, as I mentioned, is a simplex. Simplex is a specialized data type implemented in stan, and we will generate it from a Dirichlet distribution with unit probability for all samples. And in the and so we will be generating the data using a multinomial distribution using these sampled thetas from the Dirichlet distribution. So we can of course perform this model prior predictive check to see will it cover what we really want. So estimating the parameters, of course, we get general uniformness of those samples that comparing the data to what we've sampled. Actually, all these actual data is possible because we've assumed that a uniform distribution on theta parameters in the prior. Then, of course, as you can see, all thetas have exactly the same marginal distribution, which, of course, comes from the fact that when one is large, other has to be small, and in the opposite. This is more visible in the case of this one nice triangle plot, which is very useful for visualizing such simple such dimensional simplexes, because we can see that what happens when with all those values which are just moving around this triangle. So depending on which edge, relation with each edge gives you the actual value. So even it doesn't look like the joint probability of all thetas is relatively uniform in the scope of all the possible values. So let's move to the posterior analysis. So we'll have to supplement our model with additional information. So we are adding the data, number of categories in results of the surveys. Our parameter is still a simplex. Our model is multinomial, and as a generated quantities, we are focusing on the statistic that we mentioned before. So what is the probability that theta1 is greater than theta2, or otherwise the values of what is the distribution of theta1 minus theta2, and we'll simulate some y's to do it. So we are computing those values as we wanted to get the actual result. Okay, so we have our data, again, three categories, our vector of data. We simulate from that, we sample from that, perform some summaries, and as we can see, the values of theta gives us 50% for the first category, so Bush proportion. The second category gives us 30% and less than 10% for the third category. And these results are really similar to the one actually sampled. And of course, samples from these models, theta's and y's, look like this. So as you can see, they are rather similar to each other. So if we want to see how our samples are distributed, we can see with black lines actual data and compare it to a model. As you can see, the model corresponds very well to the data. It captures all the behaviors very well, all of them very concentrated around the middle data point. In case of joint posterior distribution of theta, now we can see that all the samples are being concentrated in this area here, and those samples and the mean is, of course, as you can see, 50%, 40%, and 10%. So that's why how we get values from the these triangle plots when we are working. And finally, the quantity of interest. So what is the advantage of the first over the second? We can see that this value is the this value gives us the how this number is distributed, and we can get a probability of Dukakis winning. So the second candidate will be what is the we want to estimate the probability of when the advantage is smaller than 0. So when the second value is greater than the first one, and we could divide it by our number of our samples, and we get very nice result of 0.00025, which gives us virtually no chance of winning, which is consistent with the historical truth, because George Bush Sr. has won that election. Finally, let's move to the final example of today. We'll try to see how those complicated models with multiple parameters can arise from complicated, more functional relationships, even starting with a symbol. And we will consider so-called bioassay experiments. This is also an example from literature, which my point is that we have rats which we are being given doses of certain compounds, and we have the results of our example is what is the is given by an outcome like usually like will it survive or will it die, will have tumor, we won't have tumor, and we'll get data of consisting of dose levels, number of animals, and number of animals which, for example, survives with a positive outcome. How many positive outcomes in the end trials was obtained by giving them the dose. And we will consider creating a model that will represent this behavior. So we try a model that will model the relationship between dose and effectiveness, or let's say estimating the dose when the animals will be dying. We'll be using ribbon plots, which you've seen before. This is a quantile plot that the ribbons farther away from the middle, which is the mean, represent quantiles of appropriate levels. In case of we have a small data set, which will be absolutely enough for us. We get 4 doses in which we had 5 animals in each sample, and we observed, depending on the dose, which is given on a logarithmic scale, that's why it's in negative values. It's either 0 or 1 or 3 or 5 dead animals, and seeing proportion of this has a sigmoid-like shape. So this is something that we will have to consider. So using the logarithm, our dose gives us a logarithm of grams per milliliter, we can see the proportion of that is kind of sigmoidal. So generally, we can formulate some assumptions, and this is something which will also be a part of your model. First of all, we can assume that outcomes of 5 animals within each group are exchangeable. That is, when we have one group of rats which were given the sample, it is irrelevant from as which rat was which. So we assume that all those rats with the same experiment were, let's say, in practical point, indistinguishable each other. So their order, for example, doesn't matter. So we can model them independent, each of those rats with each group independently. So that gives us the justification to use the binomial likelihood that given that we are interested in probability that we'll get a result of y deaths in n experiments. And of course, we have to create some kind of representation of how this theta depends on the size of the dose. And what is the popular approach is to create some kind of a model that, oh, I see someone came to watch with us here. I'm very happy that someone is watching. Generally, as you can see, there are not too many people, but still something is going on. And generally, we want to create a functional relationship between the dose and the probability. And of course, this is one of the fundamentals of Bayesian statistics, that we formalize those relationships parametrically, that there's a dependence of the value of interest on predictors in some kind of parametric way. Often used is, of course, the linear dependence. So the dependence in case of that theta could be linearly dependent on x. So there will be some kind of base value plus a proportional relationship to x. But of course, we have this limit that theta has to be between 0 and 1. So we can use logit representation. So here we are, our model reached number of two parameters now, because these parameters were created using functional relationship. So our predictor is influencing the probability using two parameters that we want to estimate, and those two parameters, I will assume that will be common for the entire all the rats and specific combinations. So we assume that the behavior in each experiment is similar, but within each experiment there is exchangeability. And so this functional relationship will be that a logit function of theta I is given by, is represented as a linear function. So theta I will be an inverse logit of this value. So our likelihood takes the form of binomial likelihood, of course, with setting up, instead of theta's, inverse logit of this linear relationship for each vector of parameters. So size of sample, dose, and the observed number of deaths, which leads, of course, to a posterior where we have some prior for those regression coefficients, which is because it is essentially a logistic regression, but not as a classifier, but to represent the percentage, the actual discrete events in a finite number of trials. So we have those parameters and the likelihood of each of the experiments individually, because again we have this interchangeability, so we can work on those separately. So how to select the prior for regression coefficients? And again, we can go, for example, to StatWiki to consider, for example, using the it's recommended to use a student distribution with zero mean and some information about scale and not too large number of degrees of freedom. But of course, we can use also we can also use normal distributions with small spreads or stuff like that. Here, it won't make that much of the issue. We are using the this, of course, here is relatively simple case because the doses that we are using here have small values between 0 and between -1 and 1. So in this case, this prior is generally okay. The problem is that the more, we'll see it in an example in the next lecture, that the more samples from the more predictors in logistic regression, the smaller spread on the parameters of the smaller spread of the priors has to be given, because otherwise our model will get saturated very easily, and it will be difficult to capture the behavior inside the interval. So, without further ado, let's move here to our model. We provide our model with data. We provide it with priors. We create our model that will be, of course, computing the binomial distribution, fitted with appropriate theta given by an inverse logic. So we can sample from our, we can compile our model. We can provide with data, set up the chain experiment for the prior predictive checks, because again, this is the prior predictive check option, and we can see that when we have a non-informative student prior, we will get a large spread of parameters, and that causes us that we have over-representation of values between on the edges of the possibilities of either all die or most of them, or all die or most of them survive. This, of course, comes from the problem of the problem that those parameters are a bit too large, and that's why it pushes us to away. So we should probably add a smaller scale. But in this case, we are not dipping too much, because as long as there is something happening here, it's okay, because our model will be able to recover actual parameters. If it's nothing happening here, then of course it will be very hard to explore that part of parameter space. The safest selection of priors is to set them up so that prior predictive distributions will be generally uniform, or at least allow values in all the scales for all the values that we are interested in. Okay, so we can see how the samples from our distribution work. So we are generating those sigmoids that correspond to the our relationship between those and that number of deaths, and using a ribbon of those quantiles, we can see that it is generally too broad. It is too broad, as the median doesn't capture those LNC, but it's not terrible. We won't be focusing on that today, but if we could do much better prior selection to represent the data better, with still providing reasonable give to estimate parameters. When we move to the posterior, models of course has to include parameters. We are computing using the transform parameters. We'll just compute the thetas. We use the same priors. We could use much smaller scales, and probably would work better, but it's not that horrible anyway. Which you can see sampling went rather well. We get the we'll see how samples look like, and you can see the posterior samples concentrated very strongly in this area, with prior samples being much more having much more spread. Alpha and beta parameters, marginals of them, give us that alpha, so the intercept is relatively close to 0, and the effect of beta is around between 7.5 and 10. Which of course we can use the instead of samples, we can use the kernel density estimator to create such nice plot. But the problem with scales is always the issue, because we have different scales here, so it looks different. When we compare it to prior predicted distribution, we can see that it's not that bad. We can capture, especially we captured lower and upper very well. In case of the middle ground, there are some more complications that are happening here. Using the same approach as previously, sampling values from here, we get a ribbon plot which very well captures the data that we wanted. Finally, similarly as previous with the election example, we sometimes want to get some kind of statistic that is, for example, decision oriented. So what is the probability someone will win election, or what is the probable value that of probable value of those that will give us 50% of deaths? So that so-called lethal dose LD50 is from lethal dose 50 is that what is the dose at which the probability of death is 50%. This can be easily computed from our logistic model because we already have all the parameter values. So we just want to have to compute the expected number of death if our alpha and beta using our alpha beta. So we are interested in these values. We select only positive beta because the relationship makes sense only when increasing the dose actually increases the lethality. So we are computing those values directly from the logit function. It is actually a very simple situation that logit function takes a value of 0.5 at 0, so we just need to compute when x is 0. So and x solving this equation, and this is the minus alpha divided by beta, assuming that beta is positive. And that gives us the distribution of the LD50 value. Remember that because LD is a logarithm, it can take the dose value is a logarithm. The LD also can take a negative value. So conditional that beta is greater than 0, so the model is at least reasonable, we can estimate the values of the lethal dose 50. And we can get this confidence interval here very, very easily. So that's a summary of this. As you can see, models can, introducing parameters to the models is not computationally complicated. The issue that we need to focus on is that interpretability of parameters might be a bit more difficult when the parameters come. Those parameters can come from specifying functional relationships, even in simple one-parameter models like binomial model. And the more parameters we have, the more difficult summarizing is. And when we look at parameter summaries, we get generally a marginal distribution of some kind. And sometimes it's often better to compute actual quantity of interest. In the election example, the probability of first one winning. In the biopsy example, LD50. So estimate the statistics that we are interested in, which are the marginal statistics of what we want. And as you can see, we don't have to do any manual integration for that. We just sampled it out and it was okay. All right. Thank you very much. Next week, the lecture will be in the form of asynchronous because I'm on a delegation. I'm going to a conference. So there will be a YouTube premiere waiting for you at the same time that we have here. Thank you very much for participation in the lecture for those that participated. Because the delay is humongous, which I've observed before, I will be answering questions directly on Teams or email. If you want something, just ask. Then the chat will be problematic looking at the delay that is currently happening. Thank you very much, and see you see you on the next. Okay, thank you.